Welcome back again. What we're going to do this time is we're going to do a software debounce solution. So bouncing, just so you recall, is when you press a push button, it kind of like it hits, then it actually bounces back up, and then it kind of hits again like this. And the microcontroller is fast enough that it actually can pick up those little jitters. If you were to look at it on an oscilloscope, those little jitters might look like this, right? This one is not too bad of a debounce. But you can see that as the switch goes from high to low, those are what the bounces look like. Once you convert that into digital, there's a cutoff threshold like right here. And so you can see that what it actually looks like is it looks like you press the button, let it off, press the button, let it off. And the darn microcontroller is so fast, it sees those. So it's the problem is present because the microcontroller is too good, right? So we've got to fix it. The best way to fix it is to simply delay when you do the reading. So if you see the edge there, wait some period of time and then do another reading out here. Typically this length of time that you need to wait, it totally varies based on the switch, but it's somewhere on the order of like 20 milliseconds or say 30 milliseconds. That's an M, by the way, 30 milliseconds. Somewhere in that neighborhood. I have seen push buttons that take like 200, and I've also seen good ones that take half that time. So we want to come up with some mechanism to delay our reading by that long. So one simple way to do it is, I kind of said the word delays, is to use a delay function. And this totally works. It's kind of simple. But we just delay a certain length of time. Since our clock is at 4 megahertz, the math is going to be pretty easy because one instruction cycle is 1 microsecond. So let's say we wanted to delay, I'll just add a pound defined in here. I'll call it debounce MS. Let's say for these we want to do a delay of 30 milliseconds, right? So 20 or 30 is the range, we'll use 30. And all I really want to do is I just want to add a delay, 10K TCY, I'll do a control space, of debounce time. So, oops, I meant to say not 10, but I meant to say 1K. So if this number is 30, and we want 30 milliseconds, then if we just do a delay of 1,000 times 30, that'll be 30,000 microseconds, which is 30 milliseconds. So if we wanted to do a very simple debounce of these guys, all we need to do is we just need to delay for 30 milliseconds, and then we're going to need to do something. Now if we delay for 30 milliseconds, then we reset the flag, and we increment the counter no matter what, that might be good enough, right? Because it'll, even if there's a lot of jitters, it'll only catch one of them. So that might be good enough. But if you wanted to be really sure about it, you could say port B bits.rb0 is equal to pressed. So not only are we going to wait, and in case there are multiple flags, absorb them, we're going to go one step farther, and we're going to check to make sure that it's still pressed after those 30 milliseconds. This can be important because sometimes when you let off, sometimes it bounces then too. But we don't want, when you let off, to call anything. I use the pound define pressed, but really I just mean to define it up here. So pressed is 0. We've used that pound define before because when you press the button it's 0. So all right, if after 30 milliseconds we're going to reset the flag, we're going to check to make sure it's still pressed, and if it is, then and only then increment the counter. So I'll go ahead and put that code down on here. I'm going to do a Alt-Shift-F to fix my formatting. And I'm going to change these to actually check the correct pin. That's a good fix. So RB0, RB1, and RB2. All right, so we should have a significant improvement in our debounce. So it's going to go ahead and build and run. And I'm going to do the same test that I've done in the past, and that is I'm going to hit the button 10 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Worked tremendously better. All of them are at exactly 10. So this solution is really all you need to debounce a switch. Just because I like to show people cool things, though, I will say that we could do a little better, and that is to use a trick called main event flags. I would say that this is kind of a little advanced topic. We won't use this in an exam, but I want to show it to you just because it is popular in microcontroller programming. And the idea is that interrupts are supposed to be fast. They're supposed to be lightning fast. So in an elegant world, which we do inelegant things all the time, you wouldn't have delays in an interrupt service routine because they're meant to totally block the main function, go in, go out, right, and be done. So really what you should do is instead you really just want to set a flag, and a flag is really just like a variable or one bit within a variable, and then return, right? So you just want to set a flag, get in, get out, would be a better way to do it. So this is very common, and what people do is they create a variable called main event flags. Main event flags, really a flag just needs one bit. So what people do is they make pound defines, so there's an interrupt 0 flag. And the interrupt 0 flag would be, bit 1 of this thing, right? And then they would make another flag for interrupt 1 and interrupt 2. So instead of making a separate variable for each flag, people get sneaky and they say, my flag is going to be one of the bits inside this long, because the long is 32 bits, so all of a sudden you get 32 flags for free. And of course, firmware programmers use binary, right? Or use hex instead of binary, which, you know how to do that, so why not? We'll write the same thing in hex. And then just to guarantee that it uses a long, I'm going to put this L at the end. Another thing, just because this main event flags is so common, is a lot of people go ahead and say volatile just to make sure that it doesn't get too smart about it. So it says, hey, compiler, never make any assumptions about this variable. Make it volatile. And then this is totally optional. A lot of people say that it's unsigned as well. That has absolutely no effect, but a lot of people do it, so I'm going to say the word unsigned as well. So what we need to do is we need to be able to set a flag in here, and the way you can set a flag is you can take the variable and OR it with, this is where the sneakiness comes in, OR it with that pound define. And if you think about what that does, is it takes that variable, and if it ORs it with this thing that has 1 bit high, it's going to just set that flag. So this line of code here literally just sets that 1 bit. And then what you do is you just finish, right? So you just say, hey, I'm done. I have done everything that I need to do. I'm out of here. I'm going to comment this out just so you've got it for your notes if you ever choose to do a different approach. And so each of these is going to just set the flag. Number 1 is going to set the interrupt 1 flag. Number 2 is going to set the interrupt 2 flag. And it's going to set that flag, and it's going to return from the interrupt. So the old solution did work fine. I would probably use the old solution because it works. But this is a more elegant solution of getting into the interrupt and then getting immediately out. Now the trouble is you have to go handle this flag somewhere, and the place where you handle it is actually back up within main. So back up within main, what you can do is you can say if main event flags, if that bit is a 1, and again you have to kind of think through what the syntax does. So main event flags single-handed with this, it will look only for that 1 flag being true, and it won't worry about the rest of the variable. And if it is true, then what you want to do is you want to do kind of some similar code to what you had before. You want to clear the flag. This one's the worst. You want to clear the flag off. If you're a hardcore firmware developer guy, the way you clear it off is you AND it with the inverse. So the inverse is a bunch of ones and a single zero, and if you AND it with main event flags, then what it'll do is it'll just clear that one off. And then what you want to do next is check to see if it's still pressed. So a little confusing. I grant you that. So we want to say this one is for 2, so I want to say is RB2 still pressed? And if it is, I want to increment his counter. So I've got to do that logic 3 times. So I've got to say, if it was from this flag, reset it, and then check to make sure it's still down. If it was from this flag, reset it, and check to make sure RB1 is still down. All right, so this is a finished app. It does debounce, and not only does it do debounce, but it is very elegant in the fact that your interrupts are very fast, and they return, and then this delay of 30 milliseconds is happening inside the main event loop. Ooh, it's not happening inside the main event loop. It needs to be happening inside the main event loop. I meant to add this delay up here as well. And now they are thoroughly debounced and elegant. There is one more improvement we could make, but I'm not going to do that in this video lecture. I'll make another one if you're really a glutton for improvements, and that is 7, 8, 9, 10. There's no reason to block for that 30 millisecond delay. You could use a timer interrupt to avoid that blocking. I'll do that in the next video lecture, but that is truly optional, right? Okay, so now you know how to debounce things. Good for you. We'll see you in lab. Bye.